This video aligns with the Ready, Set, Go assignment following the lesson Pascal's Pride from Unit 3, Quadratic Functions. In the Ready, you will be asked to use the distributive property. For more information on the distributive property, you can view the Ready, Set, Go video for Lesson 2 or Lesson 5. The examples in this Ready will require you to use the distributive property twice with two different numbers that are being multiplied into sets of parentheses. These problems are actually joined by an addition or subtraction sign between the two expressions. Remember, when distributing the 2 into the second set of parentheses, in this case, we are actually distributing a negative 2. A negative 2 times x would result in negative 2x, and a negative 2 times negative 5 would result in a positive 10. After combining like terms, the answer to this example is 6x plus 14. When multiplying two binomials, you will also use the distributive property. You will start by distributing the first term from the first set of parentheses to the two terms in the second set of parentheses. Then you will distribute the second term. In this case, minus 6, a negative 6 will be distributed to the terms in the second set of parentheses. After combining like terms, which are the middle two terms in this case, the final answer to this product is 5x squared minus 28x minus 12. Another example of multiplying polynomials is taking an expression and squaring it. In this case, the binomial x minus 6 is being multiplied by itself, since the square represents multiplying the same quantity to itself. The distributive property will still be used, and the negative 6 will still be distributed. When you combine like terms, the final answer to this product is x squared minus 12x plus 36. Since these binomials that we were multiplying were the same, do you notice any patterns in the final answer versus the original binomial that we started with? Another method for multiplying polynomials is the use of the box. In this case, our example is more complicated. We are being asked to multiply a trinomial times a binomial. In this case, the box will have to have a length of 3 and a width of 2 to account for all of the terms in the original expressions that are being multiplied together. To use the box, we will multiply the first term from the first set of parentheses by the first term in the second set of parentheses, and so on throughout the box. You will notice as we go through this top row that we are multiplying each of the terms in the first expression to the 2x in the second expression. When we look at the bottom row, we will follow the same patterns. When multiplying x squared times negative 5, we will get negative 5x squared. Then we will multiply the negative 3x times the negative 5, resulting in positive 15x, and so on throughout the box. All of the terms inside of the box make up our final answer, but there are multiple terms that are like terms that can be combined. The first term that we multiplied is the 2x to the third power. Since there are no other like terms with a third power, this is part of our final answer. The negative 6x squared and the negative 5x squared can be combined to negative 11x squared. This is now part of our final answer. The 14x and the 15x can also be combined since they are like terms. this plus 29x will now be part of our final answer. And finally, the minus 35 does not combine with any other like terms from the box, leaving our final answer as a 4-term polynomial to the product of this trinomial times the binomial. An extension of this task is to use Pascal's triangle to help you multiply binomials to various powers. The last entry in the table is a binomial being raised to the 4th power. You will notice the highlighted terms have the degree of the term in decreasing order. So x to the 4th power is in the first term, where x to the 3rd power is in the second term. Then the degree decreases to x squared, and then decreases to x to the 1st power, and there is no x variable in the last term since x to the 0 power would result in 1. Looking at an example where x minus 6 is a binomial being raised to the 5th power, we can follow this same pattern. The variables in the terms will start with x to the 5th power and decrease in degree all the way down to x to the 0th power, which is not included since it would result in 1. The next thing that we will notice is that Pascal's triangle's 5th row, 1, 4, 6, 4, 1, is included as a coefficient in front of the terms in the final answer expression. Since 1 times x to the 4th power would just result in x to the 4th power, the 1 has not been included. How can we find the next row in Pascal's triangle? Remember that the numbers in Pascal's triangle's row come from adding the two numbers above together, such as 1 plus 4 would give us 5, 4 plus 6 would give us 10, and so on, with 1s on the outsides of the row. These numbers will be included in our expression as coefficients. Again, the 1 is being skipped since 1 times x to the 5th power would just result in x to the 5th power. The last pattern to notice is what happens with the plus a as we multiply out the binomial in the table. You will notice that these degrees of exponents are actually backwards from the variables. The very last term will have a to the 4th power, and then the degree a to the 3rd power will be in the term before. Remember to start with a to the 0 power, and so a to the 0 power is 1, which is why it's not listed in front of the first term. Our value for a in this example is a negative 6. In each of the terms, the degrees are increasing by 1, starting with negative 6 to the 0 power, which is not included in the first term since it would just be 1. In the second term, we can use negative 6 to the 1st power, in the third term, negative 6 squared, and so on. Remember to be careful when working with your signs because negative 6 to the 1st power is negative 6, whereas negative 6 squared is actually negative 6 times negative 6, which is a positive 36. We will now just work on simplifying each of these terms to find our final answer for the product of x minus 6 to the 5th power. As we start to look at the terms, remember that we are taking in this next example the 5 coefficient from Pascal's triangle times negative 6 to the 4th power times x to the 1st power, which will result in 6,480x. And finally, negative 6 to the 5th power will be a negative 7,776. This is the final answer to x minus 6 to the 5th power. Using Pascal's triangle is a much more efficient way to come up with this answer instead of having to multiply out x minus 6 times x minus 6 times x minus 6 5 times. In the Go, we will look at congruent triangles. Recall that there are ways of knowing that triangles are congruent, such as angle side angle, side angle side, side side side, angle angle side, and finally hypotenuse leg. If you are not given this criteria when looking at two triangles to determine if they are congruent, you may not necessarily know that they are congruent if you have been given all three congruent angles, side-side angle, or less information than any of these. Let's take a look at this example. Is triangle SRT congruent to triangle BAC? All three angles are marked as congruent in these two triangles. However, angle, angle, angle is not a way to know that triangles are congruent. They might be congruent, but we don't have enough information to justify that claim. In this example, is triangle ABC congruent to triangle DEF? Angle B and angle E have been marked congruent. Angle C and angle F have been marked congruent, and their included side has been marked congruent. Yes, these triangles are congruent by angle side angle. In this example, are triangle CAT congruent to triangle DOG? Do we have enough information to determine that these triangles are congruent? Only one side has been marked congruent, which is the base of each triangle. This is not enough information to guarantee that these triangles are congruent.